Hello all, good morning. This is Dr. S. Subbalakshmi, Assistant Professor in the Department of Mathematics, SNS College of Technology. This is a lecture video series on the course Probability, Statistics and Numerical Methods, and now we are on to the topic Runge-Kutta method. This video serves as a case study for Runge-Kutta method. Introduction. Coming to our Runge-Kutta method. Runge-Kutta method is a numerical technique used to solve ordinary differential equations. Ordinary differential equations we have already discussed about it, and it is widely used towards accuracy and efficiency in approximating solutions. In Runge-Kutta method, we usually approximate the increment value for all the given conditions here, especially useful in real-time systems where analytical solutions are difficult. In real-time systems, we apply Runge-Kutta method as discussed in the previous videos. This is a problem definition wherein we have the ordinary differential equation here, which is dy by dx is equal to f of x comma y, and we have an initial condition which is y of x naught is equal to y naught. Here our objective is to compute the approximate values of y at discrete points, wherein the discrete points will be given by x1, x2 and x3, and h2 should be the step size, which is the incremental value. So this is what we have as the problem definition for ordinary differential equations. Now, in the first step, we are going to find the case study for aerospace engineering. The Runge-Kutta method, especially the fourth order Runge-Kutta method, is used to model and simulate the motion of aircraft and spacecraft in real-time environments. So, here the simulation of aircraft and spacecrafts can be done using RK4 method, since it comes under an iterating processes. Second step will be the flight simulation, how we will simulate the flight. Modern flight simulators need to replicate real aircraft behavior with high accuracy, which means a demo model should be like to represent the original models here. So it should be the highly accurate concept of doing the simulation. So aircraft dynamics, which means the pitch, roll, yaw, altitude, velocity, these are all the aerodynamic concepts are governed by nonlinear differential equations. So these concepts are done by the nonlinear differential equations, but here the ordinary differential equations is used here to numerically integrate the concept. Numerical integration can be used used for this performance of RK4 method, and this allows a real-time response to control inputs like throttle, rudder and turbulence. These are all the aerospace engineering concepts, throttle, rudder or turbulence. We all know this actually. And missile and rocket guidance. Accurate trajectory prediction is crucial for targeting and path correction, which means trajectory is nothing but a starting point and an ending point, wherein the curve will be like a parabola. RK methods are used in on-board computers to compute position and velocity over time. We know what is velocity, the speed over time, and solving differential equations, which is the second order differential equation, wherein we have a two dependent variable and one independent variable for future to estimate future positions. Now, the altitude control systems. In the aerodynamic concepts, we have altitude control system also, wherein the satellites and spacecraft use gyroscopes and reaction wheels for orientation. So, these are the two important things to be noted here. For orientation purposes, gyroscopes and reaction wheels are used, and Runge-Kutta method is always used for solving the orientation or ordinary differential equations. So, such ordinary orientations can be solved using ordinary differential equation using Euler's equations of motion. So the science is implemented everywhere here. The stability and precision of RK4 make it suitable for controlling algorithms. So the concepts or the finding of values of K1, K2, K3 and K4 makes the method suitable to work for control algorithms. This is an overview for the case study here, which is an aircraft simulation. It balances the speed and accuracy. It balances the speed and accuracy, and it is crucial for real-time onboard systems with limited computational power. As I have said you earlier, the simulations are done with much precision and accuracy, since it has to be applied on the real-time as a demo model. So that speed and accuracy can be done using this case study on aircraft engineering using Runge-Kutta method. And in more stable than this Runge-Kutta method is more stable than Euler's method, but are not as heavy as more complex and implicit methods. This is not heavy like some implicit methods. Also, implicit means not explicitly saying the values of the variables or not explicitly giving the values of the conditions here, initial conditions. So, here is an example regarding the aircraft simulation. A system simulating vertical launch motion of a rocket. We all know the rocket launches vertically. So this is a system which is simulating, which means it is trialing up a vertical launch of a motion of a rocket that can be given this using this particular ordinary differential equation, where this ordinary differential equation have the variables as thrust, drag and mass, and g will be the gravitational acceleration. We all know all these things. We have mentioned this in the ordinary differential equation. This ordinary differential equation with the initial conditions of 0, 0, we can find the Runge-Kutta methods at incremented value on vertical launch motion of a rocket. This can be simulated using this Runge-Kutta method in the next incremented steps. So, this is an example or the case study regarding the Runge-Kutta method in system simulating vertical launch motion of a rocket. So, on the whole, on the conclusion, Runge-Kutta method in fourth order computes velocity and position iteratively using time steps, allowing simulation of ascent trajectory in real time. What is a trajectory? Before itself I have explained. Trajectory is a path formed by a point to the other point. It will just perform like a parabola or a U-shaped curve. This is what here we conclude that RK4 computes velocity and position iteratively using time steps, allowing simulation of ascent trajectory in real time. So this is what a case study in RK4 goes like. Thank you.